because the exam is on Thursday, I'm going to do extended office hours. So I'll have my regular office hours right after class. I know that a lot of you can't make those. I'll have to hang out afterward for a department meeting. I'm not sure exactly when that department meeting ends, but when it is finished, I'll kind of return to this general area, and I'll be somewhere around here, probably upstairs on the 8th floor in the chemistry department side room. I'll probably be hanging out there. You can, if you're here and you're wondering where I am and you want to meet with me to discuss anything, you can send me a text at 831-566-5233. If it turns out that you don't like me, please don't blow up my phone with dirty text messages later on in the year, because that would really hurt my feelings. All right. So I'll be on campus. I promise not to leave campus until 3 o'clock at the latest. If I haven't heard from anyone by 3 o'clock, then I'm going to take off. But if I've heard from you, I'll stay as late as you need me to.
But you have office hours after this, though?
I do have office hours after this, yeah. So after this, I'll go to the library and we'll run 11 till 1, and then I'll stay on campus for a few hours after that to meet with anyone who couldn't make regular office hours. But if you intend to meet with me, send me a text right away and let me know so that I know that I need to stay here.
But what time is the department meeting?
Yeah.
Go to those sides.
I forget exactly. Usually the department meetings run around 12, 12:30 or something like that. So it'll probably, or maybe 1. I don't know. I'll go to my regular office hours and I'll come back here and see if the department meeting is running. And I imagine the department meeting will be done by 2.
You can add some. What time is it?
I looked at the email and they didn't actually say when the department meeting was. I just know that there's this mythical department meeting that you have to go to. Okay, so what we're going to do is we're going to give a really brief lecture. I hope it's a really brief lecture. I don't want to spend too much time on it. Next week we're going to start talking about ionic solutions. So last week we talked about ideal solutions, 2-component solutions. We looked at the cases where the solvent and the solute had different interactions. In some cases, they could have the AA and BB interactions could be roughly equivalent. In other cases, they were dissimilar, and that led to certain behaviors. Ionic solutions behave much differently than kind of standard solutions. And that's because an ion has that Coulomb potential, the charge forces that are much stronger than dipole interactions or van der Waals forces that govern interactions between non-ionic systems. So when you start talking about an ionic solution, you've got a whole different kind of line of reasoning that you need to use when you analyze the thermodynamics of ionic solutions. And so we're going to talk a little bit about those systems, just kind of as a primer to wet your whistle, so that when we start talking about it again on Tuesday, you've got a little bit of a foundation built. Then after that, I'm going to talk to you about the exam. I've already written probably 60% of the exam, so I've got a pretty good idea on what to coach you on. So we'll just throw some advice your way on how to study for this thing.
This is for
I'd have to go back and dig into your book and see. Chapter 10, yeah, this relates to chapter 10. Chapter 10, we're dealing with pH and acidic solutions, which are essentially solutions of ions. But your chapter 10 doesn't necessarily cover the stuff that I'm covering right now. The stuff that I'm covering is kind of an aside. That said, it might be that I just haven't looked at the right chapters of your book to find this material. So if I find it, I'll reference it. But this is just kind of an overview of the factors that you have to consider for ionic solutions. So let me see what I wrote.
So is this stuff going to be on the exam?
This is not on the exam. No, this is just a primer for next week.
Okay.
Right? So forget all of what we are talking about today once exam time comes, and remember it again on Tuesday once that happens. yikes, that's not really working, is it?
It's fine.
Can you read that?
Yeah.
Just turn them all off.
Yeah, maybe turn off the lights.
Turn,
Yeah, it's good.
is that better?
Yeah, we'll be fine.
Okay, so, I'll mail these out to you. I'll probably put together a better set of notes than this. This was just kind of a haphazard set that I stuck in there last night. So, ions go into solution, and when this happens, the reaction, total reaction can be endothermic or exothermic, right? Do you guys remember what is the factor that causes energy to be released when an ion goes into solution, in an aqueous solution, or this is a hint, or a solution that's polar or something like
The
that?
broken bonds?
What's that?
Like the breaking of the bonds?
Breaking bonds. Okay, so you got a crystal, and you got to break the pieces, the individual pieces apart. Does that consume energy, or does that release energy?
Release.
Huh?
Release. Breaking bonds.
Breaking bonds. A bond is formed when you've got something that's at a potential minimum. If you want, so if you have a bond, you're in some kind of a valley, right? If you want to get out of that valley, you're in a low energy valley. If you want to get out of that valley, you got to put energy in, right? So two charged species come together, a positive charge and a negative charge, they form a bond, and you want to break that charge, you got to invest energy. So the breaking apart of that ionic solid requires an input of energy, right? So we know that part of that process always requires an investment. What about, what's the energy releasing step?
Reformation of the new bonds.
Reformation of which bonds?
Oh, the new bonds that it makes within the solution or whatever.
There you go. So most of what we're going to be dealing with is aqueous solutions. And we looked at this before. When you've got a positive charge or a negative charge species in an aqueous solution, water comes in and it orients its dipoles around it, right? So for a positive charge, you'll get the oxygen, the partial negative oxygen, head of the water molecule pointing towards the positive charge. And around the negative charge, you'll have the positively charged dipole of the water molecule that orients towards that. And when those dipoles come in and approach those charges, it's the reverse of what happened when you had to break those molecules or the crystals apart in the first place. And you were separating positive, negative charge when you broke the crystal, the solid crystal apart, and now you're bringing positive and negative charge together when you allow water to orient around the ions, to solvate the ions, right? So if you had your crystal sitting like this, put energy in, and you can separate these guys, right? And you just throw a bunch of water on top, let the water orient, and then you get energy out. And depending on which one of those processes is the most energy, you'll have a reaction that's either endothermic or exothermic, right? If it costs you more energy to break those crystals apart than the energy that you get back when the dipoles of the water reorient or solvate the ion, then overall the reaction will be endothermic. And that'll be the kind of salt that you can make the cold packs out of. You crack the thing and the salt goes into solution and it gets cold. If you get more energy out here than you put in here, then you'll have an exothermic reaction that releases heat, right? This is actually relevant to exam material. In the case that you have an endothermic reaction that happens spontaneously, you know that for an endothermic reaction, delta H is positive, right? What must be true of the T delta S term if that reaction is spontaneous.
Must be greater than, the magnitude must be greater than delta
Yeah,
H.
it's going to be a negative, and it's going to be a value that's larger than the delta H term, the T delta S. So a lot of these salts go into solution spontaneously, which means that delta G is less than 0. And if you've got a thing that's an endothermic reaction, which means that delta H is positive, then it must be that the entropy change is large enough that the entropy outweighs the enthalpy term in the delta G. So it makes that thing happen spontaneously. So every different ion that's out there, negatively charged ions, positively charged ions, they all have their own kind of specific ways or characteristic amounts of energy that they release when they go into solution with water. And they have their own characteristic amounts of entropies. Enthalpies and entropies give you the Gibbs free energy. And this leads to terms that we refer to as delta H naught of solvation, delta S, or actually S of solvation, and delta G naught of solvation. All right, so every ion, and we'll talk a little bit about how they vary or why they vary, but every particular ion has its own characteristic delta H of S and delta G of solvation, which means that they all release or absorb a certain amount of heat when they go into solution, etc. We're going to refer to the solvation steps. You guys are laughing back there. It makes me nervous as all heck. I don't have anything hanging from my shirt, do I? Okay, just want to make sure. All right, that's okay. I didn't mean to focus attention on you. Sorry. So every single ion has its own characteristic energy or energetics associated with the solvation process. And right now, we're going to focus just on the solvation process. The solvation process is when the solvent orients around the ion. I'm not talking about breaking apart of the crystal right now. We're kind of setting that part aside, and we're just looking at the energetics of solvation. So how might we go about measuring the delta H of solvation? Well, I should have had a better set of notes, but anytime you've got a delta H, you've got H of the products minus H of the reactants, right? And so your products are gonna be the solvated ions, so we'll call this H of the positive ion plus H of the negative ion minus the H of the reactants, and the reactants are going to be whatever the solid is that, whatever the ionic solid is that goes in, or if it's not an ionic solid, it might be something like H2 gas going on to form H plus or something like that. We've got tabulated values for the delta G's, the delta H's, and the S's for a lot of chemical compounds, hydrogen gas, and these things. But what we don't have are values for the actual solvation energetics, the enthalpies and the entropies and the Gibbs free energies. So if we know, say for the case that we have Cl2 plus H2 gas, going on to form 2 molecules of HCl aqueous. And we've got a value for the bond energy of the Cl2 and the bond energy of the H2. And we know how much energy is required to separate those guys from each other. If we then take those species and throw them into solution and let them solvate, and we measure the delta H of the process, the total delta H, by measuring the heat that comes off at constant pressure, then we'll have some total magnitude for this term, right? This delta H. So if we measure physically how much heat comes off at constant pressure, that gives us a delta H for the reaction. If we've got the tabulated values of the formation enthalpies of the precursors, the reactants, then all that's left in our term that's undefined is the formation enthalpies of the ions, right? So we measure the heat that comes off at constant pressure. We look up at the tabulated values of the enthalpies of formation of the reactants, and the only thing that's left in our term is the enthalpies of solvation for the species. And we know that the sum of these two terms is whatever the difference was between our measured enthalpy and the tabulated values of the reactant enthalpies, right? Does that make sense? But where's the problem? The problem is that we have one value of energy, one value of energy difference between our measured value and this, and we know that that's equal to the solvation enthalpies of the positive ion and the negative ion, but that doesn't really tell us the relative values of the formation enthalpies, or the solvation enthalpies, sorry, of the individual ions. It might be that the negative ion going into solution and becoming solvated by the water molecules released more heat than the positive ion. It might be that the positive ion being solvated released more heat than the negative ion. We don't know which one did more. All we know is what the sum of that heat value is for the reaction. And so there's two ways that they've gone about trying to tackle this problem. And one is to simply kind of define the H naughts of solvation of hydrogen as 0, and the delta G of solvation of hydrogen ion, H plus, as 0, and the delta S of hydrogen ion is 0. So then you take something like HCl and you throw it into solution and you see how much heat comes off of it, and you set up a delta H equation where you look at the enthalpies of the formation enthalpies of the HCl, and you subtract those from the enthalpies of the ions going in solution, or the solvation enthalpies. And if you set, so we're talking about this right here, delta H is H naught of formation of H plus H naught of formation, or sorry, of solvation Cl minus 1/2 H of formation of H2 minus 1/2 H naught of formation of Cl2. You run this, You plug these values in from the tables, you set that equal to 0, and whatever your heat difference is, you say, well, that's my enthalpy of formation of chloride ion, right? And you attribute that energy difference to the solvation of chloride. Is that true? Is it safe to say that no energy was released when H plus went into solution and that only chloride contributed to that process? No, it's not true. It turns out that convention gets used for purposes of ease and consistency and magnitudes of derived values, but it's absolutely not true that the solvation enthalpy of H plus is 0 and gives free energy of H plus is 0, etc. So you look up in the back of your book tables of solvation enthalpies, conventional, they call it solvation enthalpies, and they're going to give you values that aren't indicative of what's actually happening energetically, right? We use them anyway. What is a better way of tabulating these values? That's what we're going to discuss here in a second. Before I go there, though, let me just finish this thought. So, if we do run this conventional mechanism and we define solvation enthalpies of H plus is 0, then we can go in and we can measure the heats of the reaction and run our little calculation and grab the solvation enthalpy of chloride ion. Now you say you've got the solvation enthalpy of chloride ion from your reaction. You can then take chloride ion and pair it with something like sodium and sodium chloride, throw a bunch of sodium chloride in a solution, measure the heat that comes off, and then run the same calculation now with your newly obtained value for the chloride ion, and what you're left with, the only thing that you don't know is the sodium. And so by using this defined H of formation, G of formation, S of formation of H plus as 0, they're able to go in and reconstruct tables of formation enthalpies of all of the ions. But they're not, those enthalpies are not absolute. And we're gonna look at what you would have to do to actually obtain a more absolute formation enthalpy. Assuming though that you were able to get the H's of formation, you can then go in and calculate the delta G of formation by measuring the equilibrium constant, KEQ, right? QEQ or line K. We know that delta G is negative RT line K. You can figure out what the equilibrium constant is, K, by measuring the conductivity. So you measure your conductivity of solution, you can obtain your delta G, and then you can go back to your delta G is delta H minus T delta S, and throw in this expression to solve for delta S. Go ahead.
Sorry, all those subscripts are of formation, right? They're F.
Yeah. I wrote formation, but we're talking about the solvation process in general. So when you look at that, know that we're talking about solvation. So you can use that conventional method to obtain delta G, delta S, and delta H for these things. Delta H you measure by measuring the heat. Delta G you grab from looking at the equilibrium constant. Delta S you can get from this, and then you can go reconstruct those tables that are in the back of your book. So if you open the back of your book right now and you look at your tables, these are tables that were derived using that convention that H plus formation or solvation enthalpy was 0, etc. But again, those are not perfect. They're not necessarily true. Something that you will notice, though, in general, is that the solvation enthalpies of more highly charged ions are more negative, and that the formation enthalpies of smaller sized ions are more negative. Why is that the case? Why might that be the case looking back at our model? I'll give you a hint. We looked at this equation, we've talked about it a bunch of times over the course of the quarter. We said that the force between two charged species is Q1 times Q2 over 4 pi epsilon naught. Actually, the energy is r squared, but the potential, we'll call it Q1, Q2 over 4 pi epsilon naught r. What that equation gives us is an estimate for the magnitude of the attractive forces between two species. And the magnitude of those forces go as the charge, right? The larger the charge, the larger the forces that those two species feel between each other, and the separation distance. So this thing, the potential is the integral of a force of the distance. So you integrate the force over the whole distance as you move from one place to another, and that tells you how much energy is spent as you move through that field potential. And so you take that integral and you come out with this term here. So that's this term is the energy that comes from integrating the force over the distance. The force goes as the charge. The larger the charge, the larger the forces. And the closer that you bring those two species in together, the larger the r value over which you execute that integral, so the greater the magnitude of the change. Well, if you have two positively charged ions, one has a 3+ charge and one has a 1+ charge, and you take a negative ion that approaches from an infinite distance and is pulled into proximity with this guy, and it's pulled into proximity with that guy. Which of those two processes releases more energy? The top, because the forces are stronger, because the magnitudes of the charges are stronger, and so more electric potential energy, more field energy is released when that negative charge approaches the 3+ positive charge than is released when it approaches the 1+ positive charge, right? And so when one of these multiply charged ions goes into solution and water molecules orient around it, again, we can just think of this process as negative charge approaching positive charge because water's got that negative dipole. More energy is released, more electric field energy is released when the water approaches a 3+ charge than when it approaches a 1+ charge. And so the field energy released is manifested as heat in the solution, and so your delta H is larger in magnitude for these multiply charged ions, right? Now let's take the case where we have two ions that are of the same charge, but that have different radii. So we'll make a positively charged ion here. We're going to say it's this big, and we're going to make a positively charged ion here, and we're going to say that it's basically this big. Now, any ion, any atom is a bunch of positive charge in the nucleus and it's a bunch of negative charge in the outside shell. You take something that's got excess positive charge, you take an electron, and you allow that electron to approach from the same separated distance from the center. So these guys start off at the same exact distance from the center.